all will be centered around micron scale. And I would like to begin with a very simple consideration. Suppose we have a solution and we want to have small particles out of this. Basically, what kind of options we have? We have two options. We can either disperse the solution, we use gas phase, air phase as a continuous phase where we disperse, or we place the solution in a liquid which is immiscible with the solution, apply energy, and we do dispersion in a liquid phase. Now, of course, such processes can find many applications. So you see particles basically incorporated in your food product, in your cosmetic product, in your drug product. And that's important to understand how we generate particles from a bulk solution. If you consider this in very simple chemical engineering terms, you will immediately see how many parameters actually influence the process. So you would like to have a particle diameter of d, and to get this, you have to consider the geometry of the mixing setup. Yeah, so this ratio in diameters, the volume between aqueous phase and the oil phase. Now we introduce a little bit more terms. Aqueous phase is what you want to disperse, and oil phase is your continuous phase within you want to disperse, the phase within you want to disperse something. The ratio of in viscosities also makes sense. If your liquid is your solution is very viscous, it's more difficult to get smaller particles. How much energy you put, so how many revolutions per minute you do, whether you have surfactant added or not, because we know the surfactants stabilize things at the phase boundary. And of course, the more surfactant you add, the smaller particles you get. So you can all summarize this in a certain way in such equations. So that's what we are talking about. Is called emulsification. It's a process where we produce an emulsion. One liquid is emulsified in another liquid. So this liquid, which forms droplets, is called dispersed phase. We have dispersed this phase. In a continuous phase, which is in our case oil, so you can think this about oil, plant oil, for example, rapeseed oil, and aqueous phase. This example is, for example, vinegar. Yeah, so then you make something delicious, and you like to disperse vinegar in an oil phase. A very simple example I'd like to discuss with you a little bit more in detail is milk homogenization. It's exactly the same idea what we just discussed. So you have a bulk phase, which we call continuous phase, and we have to disperse oil droplets in it. And oil is actually not oil, it's fat, it's milk fat. And when the milk is homogenized, so the particles are very well dispersed in the liquid, it's called homogenized. Basically, if it is not homogenized, it's called whole milk, or in Germany, we also have a very explicit labeling on the milk package. So that's just to give you an idea how much fat, milk fat we can have usually. So in the States you have standards 2.5, 5, and 8 for the whole milk. So usually this is like sort of native milk. And then you see that the protein amount remains the same, but the fat amount, when you go from whole milk to skim milk, decreases from 8 to 0. So obviously, if you leave milk on the bench, then you're going to see phase separation. So we're going to see creamy layer on top of the milk. And if you like properly separate this milk fat from the whole milk, you get something like this. So the challenge is, if you're thinking about mass production, is to stabilize such fat within the liquid so it remains stable for a long time, not for a few days, but really for weeks and months. So how we go about this? So we apply homogenization. Look, the principal idea is extremely simple. So you have an unhomogenized milk product in general case, and you pass this emulsion, coarse emulsion, yeah, because the particle size is very high, through a gap, which is a very small, distance between the forcer, which is a stationary part of the equipment, is just 0.1 millimeter this gap. So what you do when you pass this liquid through such a small gap, you create very, very high shear forces. So basically, you apply forces to each droplet so that you basically shear and grade them down. And under certain conditions, droplets not only get kinetic energy, so they don't only start moving faster, but they also experience what is called in this nice breakup. And then you get smaller particles. Obviously, this process can be run in a continuous way, so nothing stops you from continuously pumping your unhomogenized milk through a small gap. Surely you have to apply relatively high pressure. Pressure here and here are very different, so we're talking about tens of megapascals, so it's hundreds of bars actually, and that simply can be explained because we have a relatively small gap. Just try to push a big amount of liquid through a small gap, so you of course have to apply a lot of mechanical energy. So the liquid speed is relatively low here, it's relatively high here, and of course the highest speed in this gap. So we slowly coming to the very, very essential idea I want to illustrate with this example. An idea is as follows. We can maybe take a look at the industrial milk homogenizer. So you basically see that it has a few pumps, so they work in parallel because you do it in steps, in stages. So you first take the coarse emulsion, so relatively big milk, fat droplets in the continuous phase. You first make the first stage, coarse homogenization, and then you do fine. Then there's this equipment can work in a continuous way under sterile conditions. What I want to discuss with you and what I want to give you an idea about is if you want to apply energy to a certain amount of liquid, you can think about concentrating this energy in a very, very small gap. And by doing so, you will get very, very small particles. Here, for example, in the example just from the very, very beginning, the distribution of energy is not that homogeneous. So the speed of the liquids is highest here, but is not that high here. So people speak about dead zones where the fluid velocity is not that high. So maybe it's not that good idea to use batch, to use big autoclaves, big reactors, because in these big machines you can't really supply energy to, in our case, to break down particles homogeneously. So there's going to be always an energy distribution. In this example, the energy which is applied to all these big droplets is concentrated, so to speak, in a very, very small gap. So it already, brings us to the very, very fruitful idea. Okay, if you want to do something homogeneously, maybe you take a very, very small volume and you concentrate all your efforts at this small volume. Of course, what you can do, you can take not fat and oil, you can take another system, and that's what is very, very often used in food industry. Food industry is mainly industry of biopolymers. So you have many of them. They can be derived from plant sources, they can be derived from animal sources, they can be also of very different chemical nature. They can be polysugars, for example, like pectin, or agar. They can be also prot in nature, so gelatin, for example. They can be also phenolic compounds, for example, lignin, which comes from wood. Yeah, they can be charged, for example, alginate carries COO minus charge. They can be neutral, like cellulose or starch or agar. They can be, anionic and cationic, depending on what kind of nature of functional groups this polymer backbone predominantly has. As all basically what we can consume, and we know many food stuff based on such biopolymers. Biopolymers are very interesting because you can do what is called gelation. Many biopolymers can be brought into so-called gel state. What is gel? Gel is a three-dimensional network made out of biopolymer molecules. It also can be DNA. So DNA can also be gel. Proteins can be gel. So when you boil an egg, a chicken egg, what you do, you by heat-induced process create a hydrogel of egg white. Agar, gelatin. In the case of gelatin, you have to cool down. So you take 1 gram of gelatin, 99 grams of water, you dissolve it at high temperature, then you cool it down, and then you get a sort of a pudding, stable gel. The chemistry and physics behind gelation can be very, very different. We're talking often about physical gels. So in physical gels, polymer molecules just self-agglomerate because of hydrogen bonds. They can be also chemically induced gelation. So you can introduce cations, for example, in case of alginate, you have to introduce calcium 2 plus or divalent cation, which cross-link, say, two polymer chains. So these two polymer chains are shown here, and the cation acts as a junction, so to say, creates a junction zone between these two polymer chains. You can also create gels by changing polarity of the solvent. So if you have a poly sugar, it's a very common process as well. If you place the solution in a non-solvent, for example, in alcohol, so alcohol starts diffusing inside, substitutes water, and what happens that the polymer starts to form structures because it doesn't like ethanol that much as it likes water. What happens? It forms a solid matrix, which you would call gel. So biopolymers are very, very, and actually when you eat like, a very viscous yogurt is not because it's a very high quality yogurt. It's often actually high quality yogurts, quite fluid, but just a consumer expectations that the higher the quality of yogurt should be, the more viscous it should be. So and people just add some biopolymers like agar, for example, or alginate or pectin, just to make it look more viscous. But also, teddy bears, various puddings, factory, everything is based on biopolymers. Hanging a little, just give it a second. Yeah, that's an example how you gel alginates, so sodium alginate solution. This stream, and you introduce it into calcium chloride gelation bath, and then after a few seconds, this is exactly the process which is shown here. Calcium cation cross-links alginate chains, and you get this hydrogel in a few seconds. It's very, very fast. If you just to summarize what sort of triggers you have to induced gelation in biopolymer system. So you can think about physical and chemical ones, as we just discussed. So you can cool down solution, you can heat up. You also can apply laser irradiation, for example. In case of chemistry, you always have many options. Don't want to go into details. It's not that. I want you to hold the following message. So various biopolymers can form solutions gel. That's, for example, another way how you add cross-linker to a biopolymer solution, which is now dispersed. Yeah, so you add droplets, which when collide with the biopolymer droplets will form a gel itself. Yeah, so polymer molecules are separated here, and then they are cross-linked in the gel. When we're thinking about what sort of particle generation techniques you have, you again coming back to the same idea. Whenever you want to make particles, you have to decide what's going to be your continuous phase. It can be air, then we're talking about atomization. So you have the nozzle, then you just spray, so to speak, your solution from this, or you do it in a liquid phase, for example, by dripping. So you take a syringe or a pipette, and then you can of course do it in a much smarter way. For example, this is a device we have also in the lab, the so-called jet cutting process. You have a biopolymer solution in this vessel. This is applied under pressure, forms a jet which is directed to a knife, which is rotating knife. It's kind of wires which are rotating very fast, and they're just cutting this jet, and separate droplets to be seen here just falling down into gelation bath. To give you an idea what sort of particle sizes we can get by various techniques, just bring this table to you. So if we're talking about emulsion gelations, you have very small particles. When we talk about spraying, it's relatively big particles, but bigger particles you can produce simply by dripping. It's not able to be memorized. It's important to keep in mind, because many foods like processes in the food industry are based. I mean, I even didn't know, but recently we had a project with a company which produces fruit teas, yeah, like in tea bags. And I didn't know, but actually what they do, they also add small sugar particles which contain various aromas, and they're encapsulated in such things. We're going to see also a few examples later on. And I was always surprised why the tea gets so intensive color very quickly. You just pour in a little bit of boiled water, and then immediately after 2 seconds, in fact, they have aromas and various natural dyes encapsulated in the sugar droplets, so they dissolve very quickly, and then components from the tea are getting much slower extracted. So I just give you a couple of examples of flavor capsules, very often to mask the taste. So think about fish oil, which has a very unpleasant taste to me at least. So you try to encapsulate it in gelatin capsules. Instant microcapsules, microspheres and microcapsules. So when you have, for example, coffee extract on it, various things. So when you just want to dose something very precisely, for example, for sport food, many products you find biopolymer beads, biopolymer particles, which are loaded, yeah, by something. What I want you to also to keep in mind when we do this emulsion gelation, as I mentioned, we have a quite inhomogeneous distribution of energy in our system. So we have highest here, so more energy supplied in this zone compared to this zones, yeah. And that's why we never get very homogeneous particle size distribution. It's a real particle size distributions we've got in our lab for one project. So you see, especially for the blue line, yeah, for the straight line, how many various generation of particles are present, up to almost 1,000 micrometers, so up to 1 millimeter from something like 3-4 micrometers. So they span a very big range. When you spray, is better. It's something like this. Nevertheless, you always have this particle size distribution. This is exactly because you can't really supply energy homogeneous in such a way. I want to bring you to the idea that if you want to do a very precise control of the particle size, we want to have a very small place where we actually produce these particles, very small zone where we make the particle generation. And that's exactly the example which very close to the topic of our day lectures about microfluidics. So look here, is a very small device, 600 microns scale bar over here. So you supply solution liquid here, and you have oil phase. So, and you push a little bit oil phase just to separate one droplet, and then you again supply a little bit of solvent here, and then again a small portion of the oil, and then by doing so, by oscillating these two streams, you generate particles like this. So, and they all going to be very precisely sized. The same if we're talking about alginate can be done if you have small micronozzle arrays, so very small holes, so micronozzles, you push solution through such a micro nozzle array, then you get basically a very good control of the particle size distribution. So again and again, if you want to make something precise, think about going small, going to a micro level. We have here a classification what can be considered to be microfluidics. So microfluidics, just officially, is something what begins at micro liter, so 10 to the minus 6 liters. So this is what microfluidics usually aggregates. Of course, you just search extra information on the topic, you will see terms like nanofluidics or femtofluidics. So we're going to be talking about particles. Volumes are generally much smaller than 1 micron. Things like biochips, lab chips, actually all possible because of microfluidics, because of chemical engineering, basically, in a very small scale. What sort of advantages you get is quite clear. So as I said, you get a very precise control over the energy supply. Of course, you get low energy consumption because you have to move, you have to operate with very small volumes. Very big disadvantage of all microfluidics is, of course, the low throughput. So in these two selected applications, biochips, lab, on a chip, you are not producing something, yeah. So you're always getting an idea of something, you're analyzing something. It's rather a device than a production factory. So all microfluidic devices, of course, have a big disadvantage of having very low throughput. I'd like to give you a couple of examples of how microfluidic reactors may look like. So in the scientific publications later on, if you will be working more closely on the topic, you will see very often two types of devices like this. So here, what we want to do, we actually send the flow from the left to the right, and what happens is we want to maximize the contact between the walls and the flow. Here, we want to maximize also the path the flow goes. Here, for example, we have a mixer, so we have two flows and a very long tube where, for example, chemical reaction can happen. Imagine I have two chemical components here and I send them, they're being mixed here, so the reaction time 0 starts here, and then I can, for example, if I have a fluorescence or UV or laser or some technique which I can visualize the chemical reaction, I can see where, at what place, at what spot, what concentration of A and B I have still in the system. Almost all microfluidics operate in a continuous way. That's of course very clear. So it's very inexpensive to produce some things. It's like micro reactors. So you have a certain flexibility. That's what I mean by flexibility. Low throughput we just discussed, but you can also see it positively. So if you want to do like an analysis and you don't have that much sample, you can always create a proper microreactor system, microfluidic system for this. Well, easy to control, yeah, if we're talking about exothermic reactions. So of course the amount of heat, for example, if you mix A and B, is much smaller because simple volumes are very small. Small dimensions improve reaction rates and yields. That's again, it's more about the control, about mixing of components, because basically here you can very precisely dose your components of the reaction. No scale up issues because it's very hard to scale up. Lithography. So this is the most important, still nowadays, important process, although we have much more modern ones. We want to discuss it in a second. But I want to give you an idea, because still this process is used in microelectronics a lot. The key idea of lithography is as follows. You have a substrate and you shine light on the substrate, but the substrate is coated by a photo sensitive compound, which is shown here as a gray layer. And you basically modify chemical compounds here, so you can make it, cross-linked, and those zones which were under the mask, which were protected by this mask, are not cross-linked. So you basically get a replica of your mask on your substrate, and then what you do is you etch those zones which are not protected by the photon sensitive compound. So you create sort of cavities like this, and then you remove this compound, this photon sensitive compound, and you are left with a pristine substrate which has, in a very defined way, cavities and channels your mask had. So then you basically have two more covers to be glued to the silicon substrate, and then you're done. Then you basically have a very simple microreactor fabricated. Now we tend to use 3D printing for many things. I'm going to introduce you very quickly to 3 of 4 modern techniques to inkjet printing, to stereolithography, so it's 3-dimensional lithography, and to conventional extrusion printing. I believe you saw once with the 3D printer, yeah, like common 3D printer. But let us begin maybe with inkjet printing. So the idea is inspired by inkjet printers. So you have an ink pot, a compound which can solidify on a substrate. So what you do, you just supply this ink with a pump to a nozzle, which can either be piezoelectrical or thermal. So liquid comes on the crystal vibrates, and you produce very, very small droplets. These droplets are getting focused by an electrode system, so they are not, in all directions produced, but they are directed in one specific direction, perpendicular to the substrate. In this case, substrate is moving, and your printing head is not. The same way as in inkjet printers, so your paper in a roll, it moves, but the printing head is stationary. And then you can, by many layer deposition of substrate, sometimes we call it drop on demand, because you can actually create single droplets if you want. So the precision of this kind of printing is very, very high. You can create a very, very fine structures on the substrate. So then you grow on the substrate whatever you need, the system of channels, your maze like structures, whatever you need. This is another technique. Stereolithography is a very, very modern technique. We have also one in our lab. It's sort of a 3D printing. I like the idea very much. Look, you have a laser or a light source, basically, which you focus in a solution. So the focal point of the laser is somewhere in the solution. This solution is photocurable resin solution. So when you shine light on this, when you supply like photons, then you can polymerize the solution, but only locally. The bulk remains the same. Only at the focal point of your laser beam, you have local polymerization. And then, of course, moving this platform on which you print, you can induce polymerization of the solution at various spots. And basically by moving this platform into X and Y direction, you can print one layer. Once one layer is done, then you move the platform a little bit down, or in this case, you just lift it up and then print another layer. So that's wet-based methods how you print materials out of various curable polymers. It's relatively fast. You can also create, of course, quite sophisticated fine structures. But the resolution here is less. The resolution here much less. And then extrusion printing. Of course, if you want nowadays, many labs which work on microfluidics, the microreactors themselves, they just use conventional 3D printing, among other techniques. So official name of 3D printing we used to see is fused deposition modeling. So you have a filament, you have basically a polymer, and then you melt it in a nozzle. You may have two or more, and then they are either being mixed or just used interchangeably, and then this molten polymer is getting deposited on the growing part, growing piece which you are printing. Then the polymer solidifies here. So you may do this passively, so you also can solidify polymer actively by putting it into a closure with a specific temperature and sometimes specific humidity conditions. Yeah, so that's how they look like. It's basically very, very simple. You can construct it yourself very easily. So you have a heating element, and before that just passed through this ring, which is for a hot ring getting molten, and then you have a small nozzle which doses the molten polymer. So the precision is determined not by the nozzle, well, I mean, to a certain extent by the nozzle itself, but also by the mechanics. Yeah, so in 3D printers, mechanical part is relatively expensive, not the nozzle, because depending on how precise you can move platform, you get certain not that high, unfortunately, resolution. So we're talking about less than 1 millimeter, of course, but not in a micron scale still. I'd like to give you a couple of ideas what sort of reactions we can perform in such microreactor systems, and like to illustrate it with our own work. So we, in the past, especially, were studying many enzymatic reactions and enzymes being selected. So what is enzyme? Is a protein, basically. So being selected as a catalyst has many advantages, because it is very selective. And when it comes to optically active compounds, it can catalyze only one of the reaction with of only one isomer. Yeah, so you have here a mixture of two isomers, and only one reacts. This is the product, and another remains in the reacting mixture. Usually enzymes run and work quite well in mild conditions because they're designed to work in the body. And you can also say that enzymes are renewable catalysts. So you can engineer enzymes, and basically you don't. You can also get it from animal or plant sources. You can engineer them from scratch. So basically, they are not catalysts which require heavy metals, or metals which are rare metals, and things like this. Of course, the issue is that the enzymes are very unstable, being biomolecules. So protein molecules tend to unfold. Unfortunately, the enzymes themselves can be affected by the product. So the best example is enzymes in yeast. Yeah, when you do fermentation at a certain concentration of alcohol, yeast basically stop producing alcohol more, because they are inhibited by the amount of alcohol they already produce. So it's called product inhibition. And then, of course, you think, okay, maybe I can get more control. Again, this idea of more control, having your bioreactor smaller, yeah, creating the bioreactor smaller. Then that's what we decided to go for. We said, okay, we're gonna create a system which has an enzyme as a catalyst. Well, we want to incorporate this enzyme into a small microreactor, but we want to immobilize this enzyme, because otherwise it simply will be washed away. So it has to stay in the reactor all the time. And that's why we first came to faced the problem of immobilization of enzymes. Of course, if you have an enzyme loaded into a solid matrix and the enzyme remains active, then you can always reuse this block. Yeah, so basically you can store it and you can reuse it later on. But the thing is that to work, basically to catalyze this enzyme, should be accessible to all the chemicals, yeah, which are part of your reacting system. And then, of course, you have to fight against some diffusion limitations. You have to fight against activity um, lost during the immobilization. And of course, there is no method. So any enzyme you want to work with, and any matrix you want to put your enzyme in to immobilize are required special treatments. So the process is mainly empiric. What comes to your mind when we talk about immobilization of enzymes? We can simply adsorb them. That's the simplest way. Fortunately, that's the way which will not work that well, because in time you will wash enzyme. Ionic binding is a good option, but ions again can be removed, can be washed away. So these classes, um, cations link the enzyme to the negatively charged surface. Being washed away, this plus is no longer capable of holding the enzyme, so the enzyme will be washed away as well. So good option is covalent binding. The issue is when you do chemistry on the enzyme, you often lose activity. You can cross-link enzyme itself, but then again you have the same issue, you lose activity in many cases. And what we decided to do, and what many other groups do, they encapsulate or so-called entrapments of the enzyme. So basically they create a matrix around the enzyme. Enzyme stays intact, but then it's basically specially constrained and cannot be washed away very easily. That's what I'm going to review in a second. This is table just keep for for completeness of the lecture. So just collected a couple of methods how you immobilize enzymes. So we have a few examples of enzymes here, and you basically, if you then take a time to read the table, and then you see how actually sophisticated they are. So you have to use certain cross-linkers, or you have to use complex formation, things like this. So it's really our science. It's not the standard methods you can just look up in the book, especially for doing science. And well, when we decided when we worked on our microreactors, we just say, okay, so we're going to create a porous matrix, sort of a gel, which allows analyzation of our enzymes without actually loss of activity. That was the main thing. You don't need an activated enzyme. And then the gel should have a certain permeability. Otherwise, products or all the reactants cannot diffuse to, and products cannot diffuse from the enzyme, and should be certainly mechanically stable, because then you're gonna go for a flowing system. You will nevertheless apply some pressure drop to the microreactor, so it should have some mechanical integrity. So I'm gonna show you the results of what we have done. So we went for the system, so-called Zoll gel system. You have a compound which can be hydrolyzed, which forms very small microparticles, and then you trigger gelation, you trigger self-assembly, of these particles for a three-dimensional network. And then all this voids, pores, if you will, sit an enzyme. So it physically bound, it's not chemical, it's black, sticks are not chemical bonds, but physical bonds, which keep the enzyme in the gel. And nevertheless, we know, for example, from electrophoresis that gels are permeable to an extent for big molecules. So gels are always a good option for mobilization. That's exactly what we do. So we took our reacting system, our Zoll system, we placed some amount of enzyme in it, and then we injected into a microreactor. Very simple microreactor. So to create gel within the microreactor channels. fill them in and to perform vigilation within the vector itself. So this is the enzyme, and then the system we worked with is actually a ginger plant because we were contracted by a company which worked with various compounds of that class. And they're quite interesting. So they are active, and the activity, biological activity, is different and depends on how many glucose units you have. If you take a closer look at this big structural formula, so what you have is you have 1, 2, 3, 4 glucose units. Yeah, so depending how many, this is a native in ginger. Yeah, and if you remove 1, 2, 3, or 4 in any position, for example, you create you leave 1 glucose unit here and 2 glucose units here, you're going to have another biological activity. So they asked us whether we can selectively get a specified given product out of this starting compound. So in other words, whether we can selectively disattach, hydrolyze this bond and get either fully glucose-free product or with a certain number of glucose units in it. And that's what we actually were doing. They very quickly found a proper enzyme for this. So you have to, of course, go for something that hydrolyzes glucose units. So it's definitely going to be glucosidases. So we encapsulate them in the gel matrix, and we fill this gel matrix in a microreactor. And then what remains to do is actually it's kind of a small lab now. What you have is a very, very small lab. Given that enzyme is stable, the gel matrix is stable, you can inject very, very small quantities, and it was crucial for the project because the amount of the extracts purified in terms of this initial compound RB1, the amount was quite small, so we could not, create a big reactor and study enzymatic hydrolysis by glucosidase. So it was very, very advantageous to use a microreactor. And then, of course, depending on the pH and depending on other extra additives, which are rather uninteresting for our discussion today, indeed, it was possible to selectively disattach either 1 or 2 or more glucose units from the compound, so basically from the initial compound. So basically what you get at the outlet of your reactor is the stream, which then you analyze with HPLC and see what sort of products you get. That's once again the entire scheme, so just to appreciate how much groundwork you always have to do. Yeah, so that's always a little bit, yeah, it's like this, your boss tells, yeah, no problem, we can do it, because he or she speaks to the top management of a company. Yeah, sure. So we have microreactors, we have everything, but then the real work begins. Yeah, so if you are to do the real work, so you have to optimize gelation protocol, and this gelation goes in alcohol, and alcohols are not the best for the glucosidase. You also may go for biopolymer, which is much more milder conditions. That's what we at the end also realized, and we also did. Then you have to inject everything into microreactor, make sure that you fill everything with bubbles in gels. The gel doesn't shrink, otherwise you have bypasses, the zones where the flow can go, not basically touching the gel. So the gel has to be very, very stable. So gel should not degrade when you do continuous operation. So when you continuously by a micro pump inject through your microreactor initial compound, and then the enzyme should be stable at that. So you have to have a protocol to make sure that the enzyme is stable. So basically, you have to inject something. Usually, you use glucose derivatives and create glucose out of this and see whether your enzyme is still active and it performs hydrolysis reaction. But that's all basically you have to do before you actually start studying the real system. Just give you an example. You don't of course need to memorize this all. But indeed, what you usually do, you nevertheless take a small reactor, static machine, acid catalyzed conditions, and you always compare what you get in your microreactor with what conventional can be done. And you see that the recovery is always lower. So I just give you one bar that we have many experiments of that sort. We always see. So we have approximately 60% recovery for the acid catalyzed conventional process. When we have this microreactor approach, we are very, very close to 100. So that's important because, as I said, the amount of the material is very, very small, it's very tiny. So it's important to get recovery high just to be above the limitation, above the detection limits. Otherwise, you basically cannot detect what you have produced. The issue is, of course, to stop the hydrolysis at certain stage to get either one glucose unit here and two glucose there, or glucose, no glucose at the opposite side, or glucose one and glucose another one is on the opposite sides, two glucose units altogether for these two products, or fully. No, it's not fully, it's one glucose unit in each. And it still remains challenging. You can quite well control this part of reaction, and you can quite well produce this F2 product, which has the glucose unit here and on the opposite side. You can find conditions. And as I said, this microreactor now is your small lab where you can do. You can basically change temperature, so you can change pH level. You can also add additives which facilitate the hydrolysis of this type of materials, and then see what happens. So basically, it's a small like working course at your hands if everything is, as I said, is optimized and ready for operation. If you take a look at the conventional process, you see how difficult it is to get a high yield. Is basically yield less than 10% for this compound, and for this compound, very, very difficult, almost impossible to stop the reaction at this RD level. So just disattach one glucose unit, which is also a very interesting product. However, in the microreactor, you can speak about yields of 50%. So that has a very important message for the company. Okay, you indeed can control the hydrolysis. You can maximize the conditions. You can maximize the yield of that was in this case RD and F2 the products we want to get highest possible yield of. And for F2, it's not that high, but given that you have also RD and F2 in the mixture, that's quite good result. So that's one example of how you can what sort of workflow you have when you want to do something in a micro reactor. Of course, this is not a success story. It's just a story which poses more questions. And the first question: whether you can transfer this knowledge to other enzymes. And the honest answer is often not really, because other enzyme may have a very different stability region. It cannot be maybe packed in the gel that's your glucosidase enzyme. It may have very bad stability against alcohol, for example. So the gelation protocol has to be changed. But well, second question: can we apply microsystems with such individualized enzymes for screening reaction conditions for other processes? This is rather an interesting question. Indeed, now the tendency is to make routine lab operations to basically shift them into robotic systems like this. There are many now publications coming. People optimize the reaction conditions fully automatically. How they do it? They also have a microreactor. They have many tanks with various solutions, and they have a system of micro pumps which dose them, but they don't try all possible options. What they do one run. They do automatic analysis with HPLC. They see, okay, so the yield is say 20%. Then the system automatically changes something in the process. For example, increases amount of acid, for example. Then the yield drops. Okay, the system thinks, no, this is a bad idea. So then I reduce amount of acid, and the yield increases. So by some very simple neural network which runs at the back end of the process, you can optimize the process very well without actually any human behind. Yeah, so the system works, and then it gives you after certain days most optimal conditions. For example, in terms of yield of a certain product. That mainly done for microreactors, because the amount of chemicals you need to use are very small, and you can automatically wash the reactor. So once reaction is done, you basically flush it with a certain solvent or buffer, something like this, and then it's ready for next run. In the batch case, you have to clean it, you have to assemble it back. No, here in microreactor you have basically everything set for the operation. So that's basically a tendency, and the reason behind this that's goes a little bit beyond the scope of this lecture is the crisis we have in science, which is called irreproducibility crisis. It means that when you try to repeat protocols published in peer-reviewed publications, then in many cases, in some scientific disciplines, over 50%, they are irreproducible. So they take a protocol as it is, take all the chemicals, all the concentrations, you do the same as what is written in the publication. You don't get the result described in the publication. What is this? Is it fake? Is it a scientific misconduct? Or is it just a mistake? Or maybe some important details are not mentioned intentionally or just by mistake, and things like this. Yeah, so this what we all see in many scientific disciplines, and that's what we want to fight against. Yeah, as a scientific community. And one way is to fully to perform experiments in a fully automatic way. Many other options. If you're interested, then we can discuss it later on. I can give you a couple of links to read about this more. Okay, so basically I'm at the end of the I'm at the end of our microfluidics lecture. We still have 10 minutes. Thank you very much for many numerous emails you wrote to me. I think we have a winner. I'm not sure. I simply had no time to go through all the emails. I think one email, I just glanced over. I saw that I did. This is pretty interesting. So next lecture I will do the full solution to the puzzle why electrophoretic mobility should be proportional to the log of molecular weight of a protein. But now I want to listen to you and ask you for if you have questions.
I have a question.
Sure.
Whatever we get in the microreactors, like if I get this is my optimum temperature, how do we transfer it to my industrial condition?
People face this problem and we basically don't know. I mean, of course, it's always good to have something than nothing, but at the end, what we do is we only use microreactors for products of very high added value. And that means that, basically your raw materials are separated by a very high amount of money from your products. So you can sell your products much more expensive than your materials cost. And that's why you can do by membering up a microreactor system for industrial production. So there are companies nowadays also in Europe here which produce microreactor systems for industrial production of prodrugs, various drugs, things what I just showed you, experimental drugs like anti-cancer candidates from various plants molecules, things like this. So if you really want to translate it one-to-one, then you have to, by numbering up, create a microreactor array, which then will be run in parallel, and that will give you the desired amount. Basically, that's the only way. Because hydrolysis, this example, if we just stick to this example. So imagine, you have a reactor, you have a stirrer, you put your all chemicals, so you have your enzyme, everything works perfectly. But you can't really stop the reaction at the certain step. So the hydrolysis always goes. And the bad thing about this particular reaction, that's the products partially hydrolyzed, they're getting hydrolyzed even faster. So then you have to, at some point, just basically freeze the system, or somehow stop the reaction, for example, by adding acid, then separate the mixture. So you basically have all the initial product in it, initial chemicals, and then you have to clean out the clay and then run once again. So it's a very different approach, and that's why people say, okay, being optimized for microreactor, let us use it in microreactor.
Okay, thank you.
Hello.
Hi.
Yeah, I also have a question with, you mentioned a lot of challenges for the development of that microreactor. Now I was curious, how much time, more or less, are we talking about to overcome these kind of challenges, and maybe how many people are involved in something like that?
I would say thousands of people all over the world.
Okay.
And that's the thing, the challenges may look very, very simple. It's like the same with global problems. I mean, how to bring peace into African countries. it seems, I mean, everybody now in his or her kitchen knows the solution, but in real life, this is really difficult solution. And not because it's not because politicians really don't want to have stability in that or this region. It's really difficult because you have many actors in this game. And also here is basically you have thousands of people, but it doesn't mean that you get the solution immediately. It may look like it's very, I mean, they're all lazy, and they do nothing. But in fact, to overcome all these challenges, you basically have to perform credible number of experiments, and you have to have funding for this. And funding may come from industrial source or from a state source. Imagine now I, being a scientist at the university, ask taxpayers that I gonna, do all the systematic analysis of all possible microreactors. This not that, this not that sexy. It's very difficult to convince funding agencies to give me money consistently on maybe on 10 years, maybe 15 years. This is you need to have certain buzzwords. And when we speak about microreactors, so is basically old-fashioned kind of a little bit of thing for for many people. And if you want to ask industry, then they say, why do we need to optimize everything? Why do we want to solve all the global problems? We just solve our particular problem. So you, being an industry coming to the university, you will act exactly the same, wouldn't you?
Yeah, sure. I guess
that's the issue. So basically, where you get money for solving this all things. And the question is, do you really need to solve all these problems, or you just by basically select all the processes which are of interest for industry, and then I mean many ways to think along many lines. One can say, okay, we at the university want to do very fundamental research, so we should not depend on the companies. Others say, no. If you do only research which is not inspired by the companies, then you basically study something what can't really make our society better, because basically only by products which are scaled up, which are sold, and which are in use, we can really bring innovation into society. And they have also a point, right? It's a difficult question when all the problems will be solved. I think never, and maybe we should not be that much worried about this.
Okay, that's interesting. Thank you.
We can have a separate discussion. This is indeed very interesting. Other questions? So then I still have to convert the slides which I show you into PDF and upload to StudIP. Then, well, it remains me to say, have a happy season holidays, Christmas celebrate, and we see each other, and happy New Year to all of you. I hope that 2022 will be definitely better in terms of travel restrictions and many other things we could not enjoy 2021. We will proceed physically. I mean, if situation of course permits, and we see each other next time, Monday, 9:45, already in Jan. So take care, stay healthy, enjoy this hopefully with your families, these holidays, and all the best for you. Goodbye.
Bye. Thank you.
Goodbye.
Thank you.
Bye bye.
Happy holiday.